23 years ago, I shared the offices of the, algebraic geometry section with Alexei Nikolaevich and the others in the Steklov Institute, and spent a year here. And when I came, I was not at all thinking about the kinds of questions I'm going to be talking about. And I don't know, I've many vivid and confusing images from that time. But what I know is that a year or so later, I started thinking about the Langlands program. And so somehow something happened while I was here. So I'm going to talk about in a search for a Langlands transform, but I can tell you right now that there's nothing, it's not going to be found at the end. It's not like Proust's novel, the end, he goes searching for lost time and he finds it, but there's nothing to be found here. But let me start. This is a mixed group, so I'm going to start with the sorts of things I don't usually talk about. So let me just remind you, those of you who are not in the CNRS or the Academy of Sciences have all probably taught courses in Galois theory, and if you have, you may or may not have noticed that there are almost no examples. You do the Galois group of this polynomial. So probably, if you teach a course in Galois theory, you say it's about finding roots of polynomials, but in fact, it's not that at all, because there's this polynomial and then there's this polynomial, and then there's the general case where the Galois group is the symmetric group, and that's it. That's the complete list. Nobody ever teaches. Maybe you can give a few other examples if you're a little bit ambitious, but that's the list that everybody learns. So then you have to ask yourself whether you have been dishonest to your students all these years, or whether there's a reason for the absence of examples. And there is, of course, a reason that there's other examples. All other examples are deep. And so they're not at the level of a first course in Galois theory. The one way of talking about it is to refer to Kronecker's Jugendtraum, which has various formulations. This is the Hilbert-Toff problem, which is to find, let me give what I think is a classical formulation of this, to find explicit generators of abelian Galois extensions of number fields. So what does explicit mean? Of course, well, here we have answers for the question. We can find explicit generators of a cyclotomic polynomial by special values of the exponential function, and this was carried out in a very short list of cases. So, of course, for Kronecker, but when I say explicit, I mean two things. First, give the generators, which may or may not. You can either think about the polynomials of which their roots are not, and then but think specifically about the explicit action of the Galois group, an action of the Galois group. So Kronecker-Weber for a number field, let's say K. So K is imaginary quadratic field, and then partly the book of Shimura Kaneyama, which was revised by Shimura without Kaneyama's name, for CM fields, which are totally imaginary quadratic extensions of totally real fields and then the list stops again. So one could either there are some ideas of Stark's conjecture and so on, but if one decides that this is as far as one's going to go with this theory, that one could drop the abelian and just look at general Galois extensions, whichever ones lend themselves to such a treatment, and Langlands in 1975, in the 75th anniversary volume for the Hilbert problem, wrote a paper with Jugendraum in the title, called, I think, Some Contemporary Problems with Origins in the Jugendraum, and he proposed within his vast program of relating number theory to automorphic forms a kind of test case, a toy model, to study the cohomology of Shimura varieties. As a generalization of this work, and he gave an outline of what should be done, and it took about 30 years, 30-some. And now it's basically done. There's still some wrapping up to do, but this test case is basically finished, and I'm going to be talking about what this does and doesn't say, and in what sense it can be considered a Langlands transform. So I should just mention that Wikipedia writes that serious doubts remain concerning the Langlands program's import for the question that Hilbert asked. So you may want to keep that in mind. I don't know who wrote that. What I'm saying may be completely irrelevant to the Hilbert problem. So let me say very briefly, what are the objects in the Langlands program? So on the one hand, we forget about the Galois groups. So on one side, you have Galois representations. So K is number field. Let me write gamma K. And we consider rho continuous representations from gamma K to GL and R, where R is a topological field, or maybe a ring. These are linear representations. This is one side. The other side is automorphic representations, about which I will become increasingly precise, but let me just say this is the spectral analysis on the homogeneous spaces of the form roughly where G is a reductive algebraic group over Q over K. It doesn't matter. So these are the two areas, two domains for which a Langlands transform is desirable, but there is no such thing. Instead, there is the as a temporary expedient that the geometry of Shimura varieties which relates to both of them. Shimura varieties are, it's completely legitimate to pay no attention to the other side when you're studying one side, and there's a whole large theory of automorphic representations, and geometry of Shimura varieties has nothing to do with Galois representation. I'm going to be talking about the connections. And so the guiding principle is that it's a familiar principle that which Eloizar had actually alluded briefly, without saying so, that the objects that look as if they should be algebraic structures that are transcendental, that look like they should be algebraic, are algebraic. So let me give some examples. So the Hodge conjecture. So we have transcendental structures that look algebraic, have an algebraic explanation, R. So the Hodge conjecture says that there's some homology classes that look like they should come from algebraic cycles, and then the claim is that they do. The Tate conjecture, which is more immediately relevant, says that cohomology classes, Galois cohomology classes in L-adic cohomology that are transform. Oh, transcendental. Yes, this is going to, as my skill with this apparatus is not so great, so it's going to be coming. Well, this actually sort of reminds me of the. I remember the blackboard so this is a blackboard that has a different property. I can't erase it. The blackboard, it's not black. Well, black, yes, indeed, but there's not another word for it. You know, even though it's a black. Yes, blackboards don't have to be black. And then there was one in the office in the old Steklov Institute which one could not actually write on it. It was very, 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 very strange. The people kept.
So I believe you complained about our work.
I didn't complain about it.
Like 20 years ago.
I didn't exactly complain about it. I brought it to the world's attention in some sense. So the Tate conjecture, and then the Fontaine-Mazer conjectures, which are less familiar, so that so rho, as before, looks if rho looks geometric, I'll state this conjecture. If rho looks geometric, then it is. Well, this is actually a precise conjecture, which I will try to state. So let me erase the automorphic representation for the time being. So what are these topological fields? Well, the most natural field to take in this place, if R is the complex numbers, then the image of rho is finite, and then the Artin conjecture. So let's always assume that so rho is always semi-simple. Let's always assume rho is semi-simple. Let's suppose, so if rho is not contained, that's irreducible, and rho not trivial, then the Artin L function is entire, which of which the modern version is that rho is associated to an automorphic representation, cuspidal automorphic representation of GLN over the field K. Now this is almost completely inaccessible. I just learned last week that practically the last case of one has any hope of proving has just been proved. It's in the process of being written down. So if n is bigger than 2 and what? If n is bigger than 2, it's inaccessible. If n is bigger than 2, or let's say k not cm, and I don't know what so for k totally real, it's now and n equals 2. This is now being written up for not for all rho, for the odd rho, or then some sign or a bad sign. So the case, this is essentially inaccessible. So let's forget about the Artin conjecture, and let me take R equals QP bar. Well, maybe even, I'm going to pretend, just in order to avoid notation, I'm going to just take QP. I mean, it's any p-adic field is fine. Well then, because this is, the Galois group is compact and profinite, then rho is the same thing as the collection of rho R from gamma K to GLN Z mod P to the RZ, the reduction mod P to the R. And these, here again you have finite image, but much more flexibility. We can either look at the individual modular representations or the whole collection and the coefficients in QP. Then, what can we say about rho? So one reason you can't teach Galois theory in the actual examples of Galois representations and in an abstract course of Galois theory is that you don't have any way to identify them. So, in order to have a Galois representation, you need to be able to know where the elements go, to be able to say anything about them. Well, if we're working over a number field, we can do this. So let's say rho, remember, it's semi-simple, is determined by its trace on a dense subset of elements. And when K is a number field, we have a dense subset of elements at hand, namely, in particular, for say gamma P, this is the conjugacy class of, I'll call this CP actually, of C, in fact, and since it's a trace, it's up to conjugacy. We have a well-defined set of conjugacy classes for almost all P. Conjugacy class of the Frobenius in the image of rho. So the trace on the conjugacy class of Frobenius is for almost all P determines the representation up to equivalence. Now there's a hypothesis. There's a hypothesis. I said, remember, I wanted rho to be a representation that looked geometric, and so I'm assuming that rho is unramified for almost all P. This is a hypothesis. I saw a picture of Chebotaryov outside. So this is theorem of Chebotaryov.
So you speak to geometric for the representation coming from some cosmology?
Yes, I'll be. So the conjectures is going to say that. Right? So this is half of the condition that the representation be geometric. The other half, remember we've chosen a prime P, but now let me just say exactly this. So this is half the condition. So rho geometric. L. Indeed, yes, almost all Q. Q. Right. L and P are going to switch very soon. So here's the definition. This had better be. There's no satisfying terminology. There's a definition, an abstract definition of geometric, but it doesn't mean. So let me just say this means that rho looks geometric. So the actual definition of geometric is as follows. Let's say X is a smooth. All these are superfluous. Algebraic variety over K, and we look at cohomology of X with coefficients in. I better stick to QP bar. I'm sure I'm going to QP. I'm going to regret it. Then with the Galois group acts. This is just the usual topological cohomology, but seen as p-adic atal cohomology. It has an action of the Galois group and an irreducible constituent. So rho is geometric. I should underline is if it is a constituent or a sum of constituent, irreducible constituent of such a cohomological representation. Okay, and these, of course, I don't know whether I need to say this, but these representations contain all the linear sort of information in arithmetic geometry.
This looks geometric.
Yes, that's half of the definition. The other half is that, well, I can define it, yeah, sure. The other half is that, so plus, so rho restricted to gamma V for V dividing P is de Rham. That's the condition. In the sense of, and in particular, it's Hodge-Tate. So certainly a representation that is geometric has these properties. This one is more or less obvious. This one is quite hard, but now it has about 4 or 5 different proofs. And the conjecture. Well, now that I've written down the conjecture, the Fontaine major conjecture. So rho looks geometric, implies rho is geometric, which is an incredibly deep problem in transcendence theory, among other things. And it's been proved in some cases, amazingly enough.
So what does rho is
de Rham. Good. Thank you. Thank you for asking. I'm not going to tell you the answer, because if I were to tell you the answer, what it means is that it's de Rham. The de Rham functor, Fontaine's de Rham functor, to the to filtered modules with Frobenius action is gives the same represent a space of the same dimension. That's what it means literally. I mean, it arises from well, I don't know, but it's a condition in p-adic Hodge theory, right? The crystalline in particular. Well, let's see. For example, I mean, this is not exactly an example in this setting, but let's say the Tate conjecture. Which Yuri Zakhin talked about, which Alexei Nikolaevich did a great deal. If x is an elliptic curve, and I'll say x, then then rho x, that's which is the representation, say over k, gamma k to GL2, well, this is P, determines x up to isogeny. Or this is the Tate conjecture for elliptic curves, and more generally, if I'll just say if rho x, so x and x1, x2 are two varieties, and let's say we have rho 1 contained in H of x1, rho 2 contained in H of x2. This means I'll put P there, p-adic cohomology. Then rho 1 isomorphic to rho 2 implies that there is a correspondence, geometric correspondence between, let's say, Z and x1 cross x2 explaining this isomorphism. So as I say, all the linear questions relating to algebraic varieties are contained in the Galois representations. So how was this, in which situation was this proved? Let's see.
I'm sorry, why is this an example of the measure?
It's not an example. It's an example of the same series of ideas. I didn't say it. Yes. I mean, there's actually a series of conjectures, about 12 or so conjectures, and this is part of what they say. I mean, this comes out. So let's say theorem for k equals q, n equals 2, and then the sign condition. This is the Fontaine-Mazer conjecture. Is true, except for some degenerate cases that haven't really been covered. Basically, I'll leave out the details. So this is due to Kissin and Emerton in two somewhat different ways, but this is based on the techniques of Wiles and Taylor-Wiles. And that's all I'm going to say, I think, about going from Galois representations to automorphic representations. They prove something more specific than that it is geometric. They prove that, in fact, because they're different statements that are called the Fontaine-Mazer conjecture, which certainly lends itself to confusion.
Is it also Fontaine-Mazer, does it also go in
If
If it is geometric, is
it
it?
looks geometric. Okay, so so the second condition is the hard one, and that's Pierre-de-Couch theory. Yeah, so that's known. I mean, that was not known.
Okay, so
I think. Yeah, I guess you could say that. Yes, yes, yes. If and only if. And I guess the point of mentioning the take conjecture is that in the setting of motives, if you can realize it as a geometric representation in two different ways, then in fact it's the same motive. That's in that sense it's that's why this and this are part of the same statement. So what they prove is actually something more precise, which is part of the general picture. In fact, a row occurs in the cohomology of a specific say Shimura variety, or more generally a Kugasato variety, but I'm going to try to avoid going into those details. So it's to prove that it is geometric, a constructive variety where it can be realized. And this is one place where one can't expect to do much more. But let me now start talking about automorphic representation. So remember, we had this row, and then we had the row of Frobenius, and I said that the traces of a row on the Frobenius elements determined it up to isomorphism. Let me write down a more complete invariant, which is a P row, which is of X is the characteristic polynomial of row Frobenius. And this is monic, degree n, and the constant term is invertible. Okay? So rho is determined by this set of PP rho for almost all P. For P outside some that set. And now I want to find a completely unrelated, an apparently completely unrelated object that also is determined up to equivalence by this kind of data. And that's where this is the automorphic representations. So, so let me see. So let's let G be GLN over our field K. And I'm going to consider pi, these are cuspidal automorphic representations. Of G of A, which are the following kinds of objects. So as I said, these are, for one thing, these are irreducible constituents. There's the formal definition, and then there's a useful characterization. So pi is contained in as an irreducible constituent of, and I'd better simplify in one way or another. This is a locally compact topological space with an action of G of A. So it occurs as an irreducible constituent of this spectral decomposition. K is G, oh, this is true, R, this is K. No, that's R star. I only need just one R star is enough. I only need one R star. There's because of the unit theorem, I only need one. This is G, G is GLN, this is RG, RK over Q, GLN, K. Yes. All groups, all reductive groups are over Q. It saves notation. But the useful definition is that pi is a collection, I mean, it's a tensor product, but it's a collection of data, pi infinity, which I won't say much about, and then pi v for v primes of k. And can people actually see this last bottom line, or maybe is there some place I should stop writing? Maybe here, for example. And pi v is an irreducible smooth representation of GLN of this locally compact topological group GLN KV on an infinite dimensional vector space, on some vector space. It's called pi v or VV maybe. And all I'm going to be able to say about this is that if pi v, so this contains a maximal compact subgroup, which is just the GLN over the integers, and if this is not 0, then it's then pi v is determined by a degree n. I mean, the set of irreducible representations with this property is in bijection with a set of degree n monic polynomials p pi v with p pi of x with p pi v of 0 not equal to 0. So now we see how these things line up. So the Langlands correspondence Langlands reciprocity correspondence. So that there's relation between rho. We say that they're associated if p rho p, and this does not depend on p, by the way, p rho is equal to, yes, actually, here k became q. I put the letter p, so let me call this v now. So, So this is Frobenius at v, right? V not an s. If p v rho equals p pi v for v, not an s. This you could say this is weakly associated, but this is what Langlands reciprocity says. It's starting from a rho, you look for a pi with this property. And just as in the Galois side, such a pi is unique, if it exists. So, the Fontaine-Mazer conjecture can be extended or complemented as follows. So Fontaine-Mazer, if rho looks geometric, then there exists such a pi, and this is basically only proved in the case I mentioned, and there's some other cases where one can prove weaker versions. But now let me look at the other direction. So given pi, when is there a row? So that turns out to be a condition on the pi infinity. Now, in order to prove the theorems along the lines of Wiles and Taylor-Wiles, in fact, one needs to understand the answer to the second question completely, because it builds on the construction in the other direction. So remember, pi corresponds to this is what this collection pi infinity to these pi b's. And Clausel introduced terminology. So pi is algebraic. Well, what is pi infinity? Pi infinity looks like a representation of a group, and it was just a minute ago, but in fact, pi infinity is a Harish-Chandra module. That is to say a Lie GLN K tensor R. Then let's say K infinity. This is, I'll call this U infinity module. So basically, it's a representation for the U infinity is equal to, so U infinity it's equal to U n to the R2 cross O and the R1. This is a product of, right. So it's this is a maximal compact subgroup. So this is a module over the Lie algebra, the enveloping algebra, in fact. So let's put this U, a module over the enveloping algebra with a compatible action as maximal compact subgroup. And once we have the action of the enveloping algebra, we have the action of the center of the enveloping algebra. So this is if the center of U of G infinity, I won't rewrite this, acts by an integral, a character with parameters in z to the whatever power, integral parameters. And then the conjecture, that's the definition, and the conjecture is if pi is algebraic, then is a conjecture. That's a natural conjecture for many reasons. If pi is algebraic, then pi is associated to some row. Some row. Right? So now I can say, what can we say in the direction of this conjecture? So here's the theorem. So the center, let me call this character. Let's call this chi infinity. So this theorem has it's due to a lot of people. So suppose K is CM field or totally real. And suppose, so that's one significant restriction. Suppose chi infinity, So this is, so we have pi, let's see, pi, a cuspidal automorphic of GLN k, and assume that chi infinity is the character of a finite dimensional representation of the enveloping algebra. So certainly, so what this means is that, so here I'm saying that this has an integral weight, but this condition is that it's a dominant integral weight. It's a regular, particular. Then there exists a row exists rho associated to pi. Okay, having, in this generality, it's not yet known whether this rho looks geometric. Okay, so let me give a list of some of the names. Late. I think I started maybe 5 minutes late, so I think I'll have just enough time to give the history. See where the Langlands transform does or doesn't come in. So when n equals 2 and k equals q, this started with Eichler and Shimura, and then more generally. And then there was a long list of people who contributed to this. So for n bigger than 2, it started with Kozel and Kottwitz. And here the condition was that pi. Now, see, if this is a CM field, then there's an element C, which is complex conjugation in the Galois group of, well, in the automorphism of K. It's a well-defined complex conjugation, and the condition is that pi C is isomorphic to pi dual. So this is where things were for something like 20 years. So then there's my book with Taylor. And then this got expanded. So here there was an additional special condition that was removed over a series of papers with Labes played an important role in this. Shin. And then it was paper with Chenevier that basically completed the construction in this setting, and there have been some additions since then. Oh, says Yoshida. Morel. So that's in this condition. That's under this hypothesis, and all of these are known to look geometric, and most of them are geometric. Are geometric. That is to say, they occur in the cohomology of some fiber variety, over a Shimura variety. That's all of these up to the last one. And the last one, here, this uses a slightly different technique, although it's a familiar technique from this theory. It had already been used in the case of n equals 2 by Delis and Serre. Uses congruences to, remember I said that this rho equals to the limit of rho r, which goes from, let's say, gamma to GLN, say z mod d rz. And basically what we were able to show is that mod r, each of these comes from geometry, but the total does not come from geometry. It's the limit in some natural space of representations that come from geometry, but from different varieties.
So the fiber varieties, how do they look like?
So the fiber varieties are Arabian schemes.
Okay.
They're the Kuga-Sato varieties. They're the familiar ones that occur in the theory of Shimura varieties. Mm-hmm. 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 So now, without this, so this is the polarization condition. Without the polarization condition, this is still being written up. This is a work of with Lon, mainly Taylor. Most of this is something that had been in the works. Some people had been talking about this. In fact, as far back as 20 years ago, Clausel had this idea, but it's being written down now. So there's a
Polarization where?
the polar without this is the polarization condition. So here there's a condition. The condition is that there's a regularity condition, which is that the infinitesimal character is the same as the character of a finite dimensional representation. And without this condition, again, the representations are obtained as the limits, p-adic limits of representations coming from algebraic geometry. But quite a bit has been lost in this construction. So basically,
So the complex structure is it unique?
oh yeah, it's a CM field, so there's a unique complex conjugation.
It's either CM or totally.
It's either CM or so either, in other words, if it's a CM field, then you have these two representations that are isomorphic, and if it's a totally real field, then pi is self-dual. That's the condition. And this condition is necessary to relate to get the Galois representations related to cohomology. So let me just very quickly say what the Langlands transform is in this setting and why it's unlikely to provide a complete answer to the problem. So let's suppose we have a Shimura variety. So Shimura variety is now going to be, remember I have this G. Now it's G is reductive. We have G of A. It's not GLN anymore, it's some other group. Modulo, well, U infinity, and I'd better put in the real points at the center, and then I take G of Q. Well, this is X infinity. This is the local, G of R. I better do it this way. Cross G of finite Adels. So on the one hand, this is not written, so that's good. But on the other hand, so rational adels act diagonally on this. Here you take the real points and you take the quotient by maximal compact and something else that's in the way, and you get x infinity, which is a symmetric space. So this is the Riemannian symmetric space attached to the group, the derived subgroup, let's say. Maybe it's disconnected. That's not so important. And now, if this is Hermitian, we assume x infinity is Hermitian. And if it's Hermitian, then this has a complex structure, and a long story, mainly forgotten. In any case, I think nobody ever teaches the proof that this has a complex structure as algebraic variety, fuzzy projective algebraic variety over a number field. So this is a quasi projective algebraic variety over, say, field F. Well, for that reason, we can now look at, with an action of GAF. So this is not really an algebraic variety, it's a pro-algebraic projective limit of such. And now, so suppose pi is an automorphic representation of G. So this is not GLN, it's G. And I define L of pi to be homomorphisms over GAF of pi f. So pi is equal to pi infinity. A tensor representation of this into the cohomology, say the alternating sum of the cohomologies of the Shimura variety. And maybe I will add some. So either I add some local coefficients, or I work in a very awkward way with this fiber variety. Well, this variety has a homogeneous structure, so it has an action of this Adel group, but also because it's cohomology, this is p-adic cohomology, say, there's an action of gamma f on here. The Galois group. So this is where the Galois representations come from. They come from the fact that this cohomology space has, on the one hand, an action of the Adel group, on the other hand, an action of the Galois group. Now, there are several problems with this picture, all of which can be solved. First of all, for n bigger than 2, the group G is never GLN because the symmetric space attached to GLN is not Hermitian. So for n bigger than 2, G is not going to be GLN. So we need Langlands functoriality. This is surely on the side of automorphic representations, this is twisted endoscopy. To relate automorphic representations of GLN and say G, and the group G that works best is this is a unitary similitude group. That's a long chapter, but it was part of one of the things that that envisioned by Langlands in the 70s. So it's all part of the same chapter that came to an end. Let's say the main missing link was the fundamental lemma. Which was proved by Baochao and Go, and that's why these results are now now available in as general a setting as what Langlands imagined. So that's one problem. Well, the second problem is that cuspidal representations. So cuspidal representations of G only give Galois representations for pi of this kind. So in other words, this means that rho both with C is isomorphic to rho, but this is not quite right. I think it's 1 minus a tape twist. I think that's the right normalization. So we get only this subset of the representations we expect, and so the new ingredient is this congruences with Eisenstein cohomology. In the sense of harder. And beyond that, if you try to remove this condition, there's no longer any imaginable connection to geometry. The Shimura varieties have given practically everything they're going to give, at least as far as the correspondence is concerned. But one can always hope that higher dimensional Adels or something. There are some methods that people are exploring that will add to the techniques. But for the time being, this is the end. This is the end. It's the end. My last sentence. But this is as far as we're going to go with this. I'll stop there. I've stopped. Mm-hmm.
Question, how to say, of a beginner on this field. So this thinks it is for number field, yes?
Yes.
But if you look in the analogous geometrical situations, so not in this sense, but for the functional fields, then you have well-established Langlands correspondence for GLN by Drinfeld and then Laforgue also using something like Shimura varieties. So this is the same kind, or it is different? So, can you compare this, but a few words?
So this is one of the topics I dropped from my notes. So indeed, what Drinfeld gave exactly the same kind of Langlands transform as did Laforgue in general. It's not a Shimura variety. It's a Drinfeld modular variety, and it's a bit more complicated because you get two copies of the Galois representation. But basically, it's the same idea. Now, and the proof is based on the same principles, namely Lefschetz formula. You actually calculate this correspondence by using Lefschetz formula, which determines the action of Frobenius on the one hand, and it's a long and difficult calculation, but it is carried out. That's most of the story has to do with that. Now, what I could add is that very recently, the word Langlands transform actually appeared in some notes of Gates-Corey, because there is a rather different approach to the geometric Langlands correspondence with complex base, complex curves, where there is a functorial transform between higher categories, not categories, but higher categories of objects, one of which has to do with representations and the other has to do with sheaves, automorphic sheaves. So there's actually an explicit functor, equivalence of categories. At least it's been announced for GL2, and they have a program for general GLN. And there's nothing in this setting that lends itself to that kind of correspondence. This is not an equivalence of categories. This is some calculation that gives you a set-to-set correspondence.
I have a small question. So you said that algebraic pi correspond to representations rho, and so can you say in terms of pi that rho is looks geometric?
So in the set, under this hypothesis, it's proved. That's so under this. So for pi that is. So part of the conjecture is that if you have an algebraic representation in Clausel's sense, then in fact it should even be geometric. It should actually come from algebraic geometry. The Galois representation will have the property. The point being that if you have a representation whose infinitesimal character is algebraic, then you can define a Hodge-Tate structure. And so the conjecture is that it is de Rham in the sense of Fontaine, and so it would be. And then the Fontaine-Mazer conjecture would say they would come from an algebraic variety. Nobody has the faintest idea where to find these algebraic varieties. But anyway, that's the conjecture. And it can be proved in this setting with this hypothesis. And there's a student of Taylor who's working on proving it without this hypothesis as well. And they're fairly confident that it's going to work.